So let me introduce Martin Heyer, who is famous for his theory of regularity structures, which was awarded by a Fields Medal and a lot of other prizes. I will not list all of them. The one more interesting thing from biography that, okay, it's written University of Warwick, but actually it's the roots of Martin Heyer are in Geneva, in the University of Geneva, which a lot of people here are also familiar with. So
I wonder why.
So the one more connection. So the talk is called very abstract mathematics of randomness, and Martin will tell us himself.
Well, thank you very much. Yeah, so well, thank you very much for coming. It's this seems to be a very broad audience. I wasn't really sure what to expect because Stas told me, oh, you know, there will be, can you give a talk to high school students? But then somebody told me maybe you should give a talk to PhD students, and then and it seems to be that there's about everybody in the room here. So we'll see. So it's
to professors.
Yes. So I'm trying to aim maybe somewhere in the middle. We'll see. We'll see how this goes. And so I wanted to tell you a little bit about somehow my area of mathematics, which is probability theory, which I think at least the mathematicians in the audience, there will be quite a few people familiar, of course, with probability theory, but then maybe some of you are not. And so especially for the younger people in the audience, I wanted to first give you a little bit of an idea of what, you know, probabilists actually do, you know, what is probability theory. Now, so of course you're all familiar with, you know, what it means for something to be random. So essentially it means that if you somehow, even if you repeat the same experiment under the same conditions twice, you would not get the same outcome. And so the only way of making some sort of predictions is to say, well, you know, you imagine that you repeat it many, many times, and then you want to get some kind of statistics of the possible outcomes. And now, one thing that you might think is that the job of probabilists is, if you want to compute the probabilities of different outcomes, of course, in a way, what we can do is not so much to compute from scratch the probabilities of outcomes. In some sense, it's mostly to transform these probabilities. So you still have to start from somewhere. And there are, in some sense, there are two guiding principles for probabilists of where to start. And the first guiding principle is something which is common to large parts of mathematics, and that's, of course, symmetry. And so in this context, well, what it means is that if you have two possible outcomes that are distinct, but that are in some sense indistinguishable from the point of view of the mechanism that produces them, then you should assign the same probability to them, right? So the simple example is this, right? So you toss a coin. There are two possible outcomes. Either it comes out head or it comes out tails. But from the point of view of the action of tossing the coin, there's really absolutely no difference. There's no reason why it should come out head rather than tail. It's completely indistinguishable, and so both of them should have the same probability, which would be a half. Of course, the other standard example is if you roll a die, then the same thing. There are 6 possible outcomes, but they're completely indistinguishable except for looking at the numbers that are written on the side of the die. And so again, they should have the same probability, which would be 1/6. Okay, so this is very, very simple to understand. And this is a very basic principle in probability. But there's one somehow much more sophisticated principle which is very important in probability theory. And that's what's called universality. And so what universality says is that, so it's a much looser kind of concept, and it's in some sense it comes more from physics than from mathematics. And it says in a way that if you have, in many instances, what you have is you're interested in something random, but that random outcome is really a combination of many, many, many different random outcomes, many little random outcomes that combine in a certain way in order to produce, the output of an experiment. And when you're in such a situation, actually very often the probabilities of the outcomes that you get in the end, those that you're actually interested in, really don't depend very much on the individual probabilities of all these small events that combine in order to produce this somehow larger outcome that you're interested in. Right? And of course, here the standard example, if I go back again to the coin tosses, so the standard example is what's called the central limit theorem. And so what does it say? Well, so if you take again, if you take a coin and say you toss it 100 times. Okay, you toss it 100 times and you count how many times you get heads. So of course on average you would get heads 50 times, but if you really do it, well, typically you won't get 50, right? So sometimes you might get 48, sometimes you might get 51, sometimes you might get only 40, right? If you're unlucky or if you're lucky, depending on how you bet. So there is still certain probabilities for the different outcomes. But now if you plot this, so here it's the outcome for, say, if you do it 1,000 times instead of 100 times. And then you ask yourself, what's the probability? So if you do the experiment, so here the red crosses are the experiment. Well, of course, I didn't toss a coin 1,000 times. I actually asked a computer to toss a coin 1,000 times, right? But then what you do, so here what you do is you do these 100 coin tosses, but then you do that experiment 1,000 times. Okay, so sometimes you get 50, so 50 would be here. Sometimes you get 51, sometimes you get 49. And so you do this kind of statistics, and you see that it more or less follows this curve. Right? And so if you do it 10,000 times, then it follows it even better. And if you do it 100,000 times, then it starts to follow this curve very, very well. And this curve is called the Gaussian distribution. And that's the simplest example of one of these universal objects that arises in probability theory. And why is it universal? Well, it really doesn't matter whether these are coin tosses or other things. Right? So if instead of tossing a coin, you take pretty much any experiment which has a random outcome, and you repeat it many times, as long as the different attempts are more or less independent, and they don't even need to be completely independent, but as long as they are more or less independent, if you make some kind of statistics like that, you're going to get a curve which is going to look like this Gaussian distribution. Right? So this Gaussian distribution is a sort of universal distribution that shows up in many, many places in probability theory. Now, so let me just go back to this question of symmetry. Right? So that was the simpler one. It seems simple enough, but actually you have to be a little bit careful. Right? So when you really want to apply this in concrete situations, sometimes you might get things wrong. So here's a very simple example. Okay, so imagine we play a game, and I have two envelopes, and there's a check in each envelope. Okay, and there's some amount of money written on the check. Okay, and the only information I give you is that one of the envelope has twice as much money as the other one. Okay, but you don't know which one, of course. And then you're allowed to, I tell you, okay, so you choose one of the two envelopes. So there's no way you can distinguish them, so you just pick up one of the two. So you open the envelope and you see how much money is written on the check. Right? So you see something, you see some amount of money. And then what do you know? So in the other envelope, well, there's two possibilities, right? So either there's twice as much, or there's half as much, because maybe the one you opened is the one that has twice as much, right? So there's either twice as much or there's half as much. And now I give you a choice. So either you keep the amount of money that's in the envelope, okay? And then, okay, you walk away with it, you're happy. Or you can change your mind and you can actually take the other envelope. Okay, but then if you change your mind, well, you're not allowed to change back, right? Because that would be too easy. Okay? So now what do? So, of course, what you want to get as much money as possible, right? So you would think, well, the two situations are completely symmetric, right? You have absolutely no information. So there's half chance that there's twice as much in the other envelope, and there's half chance that there's half as much. So how much is there in the other envelope on average? So on average, there's a half chance of having half as much, plus a half chance of having twice as much. So on average, there's going to be 5/4 as much as in the one you just opened. And so you should always change, right? Of course, it doesn't make any sense. Right, so where did I make the mistake? Right, so it seemed a straightforward application of this somehow principle of symmetry that I told you at the very beginning. Of course, why is it wrong? Well, you know, we said there's absolutely no information, and you said that there are two completely equivalent possibilities. But that's really because we're kind of silly mathematicians. I mean, you know, in reality, if you open the envelope and it says $1 million on it, you would be rather stupid to change your mind, right? Okay, I mean, if I'm already ready to give you $1 million, you would think it's pretty unlikely that I would give you $2 million. Right? On the other hand, if you open the envelope and it says $1, you know, you've got nothing to lose, right? So you can just as well change your mind and try to get 2 instead of 1, right? So of course, in reality, it's not completely equivalent because you have some kind of expectations of, you know, what kind of money I would give you. And as a matter of fact, if you think of, you know, trying to set up a proper mathematical model that describes this situation, if you really want to set up the mathematical model, then you actually have to a priori make some kind of guess of what do you believe, you know, what is the likelihood, in your opinion, that I would put certain amounts of money into the envelope? And depending on what your belief is of how much money I'm willing to put in the envelope, that would, of course, change how you would react here, right? And in particular, there is actually no mathematical model which would give equal likelihood to every possible outcome. Okay, so here it says that you think that the thing is symmetric, but there is actually no single mathematical model in which these two possibilities would always be somehow equally likely or symmetric. Okay. It turns out actually, so the interesting thing, so for the mathematicians in the audience, right, so if you want something to scribble on, exercise is, it is actually possible to set up a proper mathematical model in which when you do the proper calculation, the outcome is still that you should always change your mind. Okay? And then, so the exercise is find such a model and then explain why that one is also not a paradox. Okay? But that's a little bit more, that's for the PhD students in the audience. And okay, so you see here that, you know, one has to, So you see here that you have to be a little bit careful, right? So one has to think a little bit when you want to, it's always somehow probability theory is a nice subject, but when you want to actually apply it to the real world, one has to be a little bit careful, right? So sometimes the naive way of applying is actually the wrong way. And actually, I mean, so in this particular example, it's just somehow a silly little game. There can be situations where this has, you know, real consequences and, you know, devastating consequences. So there was a case, I don't remember, maybe 10 years ago or something like this in the United Kingdom, where a woman called Sally Clark was, so what happened is that, so she had a small child, she had a baby, and the baby died of sudden infant death. So, right, so sometimes babies, when they're very young, it can happen actually that they suddenly die and you don't really know what the reason is, and so it happened to one of her babies. And then 2 years later, she had another baby and the same thing happened again. Okay? And then some people thought that this was suspicious, okay? And so they had the suspicion that she actually killed both children, because it seems rather unlikely that this would happen twice in the same family. Right? And so there was a trial. And at the trial, there was testimony by an expert witness who was not a mathematician, I have to say. So he was a medical doctor. If he were a mathematician, he would hopefully have known better. And so there was this testimony by an expert witness who did a back of the envelope calculation, saying something along the line. So I'm slightly making up the numbers, but they are roughly the right order of magnitude. So he said something along the lines of, well, so the probability statistically in the population, the probability that a child born to a middle-class family dies of sudden infant death is about 1 in 20,000. And so the probability that it happens twice is about 1 in 400 million. And therefore, she killed her child, right? Because that shouldn't happen. And of course, it's sort of clear why the argument is wrong. So there are two fallacies here, right? So there's the first fallacy is the fact that you cannot just, so multiplying these probabilities basically assumes that it means you assume the two things are completely independent, which of course is not proven in that case, and it's likely to be wrong because there might be a genetic component, and then the two children would have the same genes, and so if it's more likely for one to die, it would also be more likely for the other one. And of course, the other fallacy is that, well, also, if you play in the lottery, you have 1 chance in 10 million of winning the jackpot. And of course, there's always going to be a winner somewhere. And so it means that that guy must have cheated because the probability that he won was only 1 in 10 million, right? So by the same argument, you would actually put the winner of every lottery into jail because the probability that they won is only 1 in 10 million. Right? And of course, things with very small probability do happen all the time as long as you try sufficiently often. Right? That's something that one often tends to forget. Right? So in a way, if a prediction says with 90% certainty something happens, and then the other thing happens, people would always say the prediction was wrong. But of course, the prediction said it happens with 90% probability, and that means that there's 1 chance in 10 that the other thing happens, and so 1 times in 10 the other thing should actually happen, right? Like, for example, getting Trump elected and not Clinton or something. So now, okay, so that was about the symmetry part. So now let me go back to this universality business. Okay, so I want to explain another example of one of these universal objects in probability theory, but which is a little bit more interesting. And so this is what's called Brownian motion. And so what you see in this little movie here is basically what you see if you take, you take water at room temperature and you put things like pollen also into the water. Okay, so tiny little particles or dust or things like this. And then you look at what happens under a microscope. Okay, and you see these particles performing this sort of very erratic kind of motion here. And so this was actually described first not by Brown. So it's called Brownian motion now. So you think it was first described by Brown, but then usually things are not named after the person who first described them. In this particular case, it's probably named after the person whose name is easier to pronounce. And so it was first described by Jan Egenhuis, who was a Dutch doctor actually, and then by Robert Brown, who was an English scientist, a biologist. And so they saw this, and so what Robert Brown thought when he saw this in the beginning, he thought that these particles were maybe, kind of little animals that were sort of moving around, which seems quite reasonable, right, when you see something like this. And he was very careful to make sure that the water itself was not moving anymore, and he waited for a long time. So it was clearly, so these things was clearly not moving just because the water around them was somehow moving and transporting them, right? And so he thought, well, therefore they must be moving by themselves, and so they must be like little animals or something. But then he figured out that that wasn't the case. And so it wasn't completely clear. So he didn't have a good explanation for it. But then, so the explanation that came up a little bit later was to say, well, probably what actually happens here is that, you have these particles that are in water. So you take one of these particles. So that's they are very, very small, but I look at it under very, very powerful microscope, so now it looks very big. And so, water, is made up of molecules. So molecules are even much, much smaller. So they're kind of little dots here. And so the idea is to say that, well, the individual molecules in water, they actually move around really fast in all directions, and they really sort of bounce against each other. And in particular, sometimes they actually bounce off that large particle. And of course, if just one molecule sort of bounces off that particle, since the molecule is tiny, 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 that doesn't really have much of an effect. But there are lots and lots and lots of molecules, right? And they go really fast, and they bounce off all the time. And so maybe all this cumulative effect would actually have some visible effect, which would make this particle move around. Okay? And so in particular, well, sort of the speed of these molecules is basically what you call the temperature. And so if you increase the temperature, you see these things sort of moving around a bit faster. And if you decrease the temperature, you see them move around a bit slower. But at the time, this wasn't clear, because actually, if you know a little bit about sort of the history of science, then in the 1830s, people didn't know for sure that water was made of molecules. Right? So these things weren't actually known at the time. So this was a hypothesis. Right? So it was something that was somehow reasonably well accepted at the end of the 19th century. But it wasn't, people didn't actually have a good experiment. Of course, you cannot just take nowadays you can take, crazy microscopes that basically allow you to see the molecules, right? But at the time, of course, you couldn't do that. And so people were looking for some sort of experiment in order to be able to make the distinction between, matter that is made from molecules and atoms and, some other type of matter, which is sort of really a continuum. And so here is so this was actually resolved, and it was resolved, well, partly, okay, so some of the tools to resolve this, so they go back to even earlier. And so they go back to this guy here, Joseph Fourier. So he was a French guy. He was kind of interesting because he was he was a mathematician, but he was not just a mathematician. Right? So he was a mathematician, but he was also a politician. He was sort of an Egyptologist, so he went with Napoleon to Egypt. He ran the Egyptian Museum in Cairo for a year or 2 years or something like that. And then he went back to France, to Isère. He was prefect of Isère, so he was kind of a relatively high-ranked politician for a while, but he was also quite good mathematician. And actually, he made 2 big contributions to mathematics and physics, which we still remember. So the first one is the Fourier Transform. And that one is sort of not so relevant for this talk, but it's actually very relevant for your daily lives. Because if probably most of you have a phone, and most of your phones nowadays can play MP3 files, right? And an MP3 file relies on the fact that every function can be approximated by a superposition of pure waves, right? So if you have a function that kind of looks like this, you can actually write it as a superposition. Here somehow they don't show. So okay, so there's supposed to be pure waves here that somehow don't show up on the screen. I don't know why. Anyway, so every function can be written as this superposition of pure waves. And this is very much used when you try to compress sound and actually images as well in formats like MP3. But the other big contribution that he did is what's now called Fourier's law, which gives you a law on how heat evolves, okay, which seems completely unrelated to what I was talking about a second ago. So what he said is, if you look at heat, so you take you take a piece of metal, okay, which is say cold, and now you heat it up somewhere, and so now it's hot here and it's cold everywhere else. And if you wait for a little bit, well, it's going to start to heat up nearby, and the heat is going to kind of spread inside this block of metal. And so you want to have some sort of prediction of how the heat spreads inside this block of metal. And well, so he wrote down an equation which tells you how this spreads. Okay? Now, what does this have to do with this Brownian motion that we had on the previous slides? Well, so in the early 20th century, two guys, one of them you might have heard of, so they independently came up with an actual proper theory of Brownian motion. So of course, right, so it was already more or less known at the time that there was an explanation like this, right? But now what Einstein and Smoluchowski came up with is a much more quantitative kind of prediction. Okay, so they came up with a prediction that then really tells you, by how much, so assuming that water is really made up of molecules, they came up with predictions of, how fast these little particles of pollen should move. Okay? And so then, now that's something that you could actually test with experiment. And now what's the link between this and, Fourier, who was on the previous slide, is that, well, basically the position of these particles is described by the heat equation. So where does the heat equation come in here? Well, say, you look at your microscope, you try to track the position of one of these little particles, right? So they kind of run around randomly. So say you see that a certain instant of time, so you see that a certain location, okay? So now you close your eyes for a second. You reopen your eyes, it's going to be somewhere else. It's going to be at a random location. Okay, so you cannot predict for sure where the particle is going to be. Right? It runs around randomly. The only thing that you can predict is the probability that it is at a given location. Right? So what you want is you want to find a way of predicting how this probability changes. Yeah, and so what Einstein and Smoluchowski recognized was that the evolution of this probability is exactly the same as this heat equation that Fourier wrote down 100 years earlier. Okay, so Fourier was, of course, not at all interested in Brownian motion. He didn't know anything about Brownian motion. Nobody had observed it at his time. But the equation that describes it is exactly the same as the one that describes the spreading of heat, right? Except that here it spreads probability instead of spreading heat. And this actually worked, right? So it came with quantitative predictions, so you can really make the experiments, and Perrin made that experiment in a couple of years later, and he actually got the Nobel Prize for that. And so this was really, so the reason why he got the Nobel Prize for it was precisely because this was actually the first experiment that proved, if you want, that matter was really made of atoms and molecules, okay? So it was a very important experiment in the history of science. Okay, so now just as an aside, by the way, so there's actually another guy here, Bachelier. So he realized the same kind of things simultaneously, but in a completely different context. Okay, so what he was interested in was the evolution of stock prices. Right? So he was really the founder of mathematical finance somehow 100 years before, or 70 years before it became kind of important. And so he was interested in understanding how stock prices change, right? So what makes stock prices evolve? And so he had a theory which was very much like this theory here. So the difference is that in his theory, well, the big guy here is the stock price. Okay? The small guys here, they are all the people who trade the stock. Right? And the collision of the small guys with the big guys every time you do a trade. Right? So every time you trade a stock, if you buy the stock, then the price is going to go up a tiny bit, and if you sell the stock, the price is going to go down. Now, of course, you know, since you are probably not a billionaire, I don't want to single out anyone, but I think it's fair to make that guess. You probably, you know, you're not a big enough fish here to really move that guy by a lot, right? So, you know, if you sell stock for, you know, normal amounts of money, it doesn't really have any effect on the stock price, right? Now, of course, if you were a billionaire, you could sort of sell half of the company in one go, and then it has an effect just because you sold it. But for normal people, it doesn't have much of an effect. But of course, there are many, many, many normal people who sell small amounts of stock all the time and buy it. And so each of these sales has a little effect, and it goes in both directions. And so it's, the picture is pretty much the same. And therefore, the outcome should also be pretty much the same, right? So you should have the same mathematics describing the evolution of the stock price. And that's exactly what Bachelier actually discovered. So he also discovered that, well, if you look at the evolution of stock prices and you look at somehow the probability that your stock price is going to take certain values at a slightly later time, well, this is also described by this heat equation, right? So it's the same object you want, that is the same mathematical object that comes up on the one hand when trying to explain what Brown saw under the microscope, on the other hand when trying to explain stock prices. So, and this is, of course, I mean, the work for which Black and Scholes got this economics Nobel Prize in the 70s is essentially somehow based on Bachelier's theory. But then Bachelier, he was sort of unlucky. He basically never even got a proper job for that theory. I mean, so I think the French probabilists didn't like him very much. And he was also unlucky because of timing with the war and so on. Anyway, so there is one underlying somehow mathematical object. This object is somehow described by the heat equation in a way. But then, of course, the heat equation is something a bit abstract, right? So it somehow describes you how probabilities evolve. What you really want to see is what do the actual trajectories look like, right? So you want to see, if you look at a stock price, it somehow, it kind of looks like this, right? So this is what a stock price looks like. And so that doesn't have anything to do with how heat spreads somehow, right? I mean, you want to have some kind of mathematical objects that describes these kind of very jittery sort of curves, which is somehow related to the heat equation. And so the first person who really did that is Wiener. So Wiener here, so he was professor at MIT. He was really the first to give a proper somehow mathematical theory from the perspective of the actual trajectories that you see, right? So it's, so technically he would construct a probability measure on the space of continuous functions, and so that you have a notion of what does it mean to mathematically, what does it mean to actually have a random continuous functions. So he's also an interesting guy, actually, by the way, because so there are lots of mathematicians' jokes about Wiener. Because he was somehow like a stereotypical kind of mathematician with his head in the air. The other thing is also, so he did lots of different things. And so he actually, of course, he's famous in probability theory because of what is now called the Wiener process, which is in some sense the mathematical object which describes Brownian motion. But then he really also became, he actually coined the word cybernetics. So the word cybernetics was invented by Wiener, the same guy. And so he was very much interested in, proper actual engineering. He was also interested in sound filtering, noise filtering. So if maybe some of you have there are these noise cancelling headphones, right? So a famous company that produces these noise cancelling headphones is Bose. Well, there's a guy, the company Bose is named after its founder, who is called Bose, and that guy was a PhD student of Wiener. Okay? And so this is, what these things look like. So let me actually show you a movie. So it sort of looks like this. Okay, so this is a Brownian motion. So this is one trajectory of a Brownian motion. Of course, it's random. And I'm zooming out. Right? So here it's one single trajectory. All I'm doing is sort of looking at it at larger and larger scales. So I'm kind of zooming out. So there are two things you see is that first, okay, so the data projector has again eaten part of my picture. But so the first thing you see is that it always somehow looks the same. Right? So you zoom out as much as you want, and it always somehow looks interesting. Right? I mean, if you take a smooth function, and it's the same if you zoom in, right? I mean, you can run the movie forward or backward. It's basically the same movie. So you can zoom in as much as you want, and it always looks interesting, right? So it's very much not like a nice smooth function. If you take a smooth function, if you zoom in, it just gets more and more straight, right? And at some point, it just looks like a straight line, and then it always looks like a straight line, and it's not very interesting, right? So this somehow always looks interesting. So it's fractal, right? So this is a kind of a fractal curve. So a fractal object is basically something that looks interesting. You know, that always looks interesting. So the more you zoom in, it doesn't get any less interesting somehow, right? The other thing you see, well, you don't see because the data projector has eaten it, but in order for this to somehow always look the same, you know, the way you have to zoom in or zoom out is that you don't zoom out the same way horizontally and vertically. Okay, so the way you have to do it is that if you zoom out by a factor 10 horizontally, if you still want it to somehow look the same, then you have to actually zoom out by a factor square root of 10 vertically, okay, not 10. Like a straight line, if you want it to always look like a straight line, you would have to zoom out by the same factor horizontally and vertically. Here, one of them is the square root of the other one. So it tells you that in some sense, at every point, it looks a little bit like a square root function, right? So it looks sort of like a function like this. Okay, so this is Brownian motion. And so actually Donska, so he's sort of well known in probability theory, but so he was the first one to really show you know, that this object is somewhat universal, okay? So in the sense that there is a very, very large class of processes that if you look at what happens at very, very large scales, they are described by this mathematical object, okay? So it's really a kind of universal object. And so now what I want to, so in the last 15, 20 minutes, I want to tell you a little bit about other kinds, so much more recently discovered somehow universal objects in probability theory, okay? So of course this story, the story I've been telling you so far is, you know, it's sort of an old story, right? I mean, so it ends more or less with Wiener in the 30s, right? So it's kind of a 100-year-old story. And so what happens, in some sense, this Brownian motion, you know, it's really just somehow a much more sophisticated version of the central limit theorem, right? So the central limit theorem was an even older story, which somehow ended 150 years ago or so. Well, not completely, actually. I mean, so there was still interesting stuff happening. But it's been understood for much longer. This Brownian motion is basically also completely described in terms of these Gaussian distributions. Okay, so in some sense, if you understand the Gaussian distribution, you know, then with a little bit of more work, you actually also understand Brownian motion very well. And so what probabilists are very much interested in is also, you know, objects that are universal, but that are not completely understood or described in terms of the Gaussian distribution, right? So the question is, you know, are these universal objects always described by Gaussian distributions or not? And they are not in general. But when they are not, they're actually much more difficult to describe. And so here is an example which has been sort of understood, well, which is still not completely understood, but which has been somehow partly, I mean, the understanding has advanced by enormous amounts in the last 10 years or so. And so this is the situation where you have interface growth models. So the situation you should think of here is something where you have some sort of two-dimensional medium, and you have two regions, and the regions are separated by some kind of interface. So there's the second picture here is a picture from an actual experiment where you take a liquid crystal. So liquid crystal sort of like what you have in the, you know, screen of a laptop also. And so you have a very thin layer of this liquid crystal. So it's essentially two-dimensional. Okay, so like the blackboard here. And now this liquid crystal, it comes in two different phases. So the same material, if you want, comes in two different phases. And they have different optical properties. So you can really see the difference just by looking at it under a microscope, right? So they would somehow look different. And one of these two phases is stable and the other one is not. Okay, so one is stable, the other one is unstable or metastable. So it's quite stable, but not as stable as the other one. And so what you do is you prepare this liquid crystal in the less stable phase. Okay, so the whole thing is in this not so stable phase. And then what you do is you take a laser and you zap the laser at the liquid crystal like this. So you sort of draw a line on your liquid crystal with the laser. And when the laser hits it, that gives it enough energy to somehow, jump into the stable state where it prefers to be. Right? So it prefers to be in the stable state, but it needs some energy to be able to jump from the unstable to the stable one. So now you have the stable one here. Or say you zap it. So you zap it like that. So now you've created a straight line of the stable one. And now that one wants to grow. Right? So the straight line starts to fatten out. Right? So it kind of gets fatter and fatter as it invades the other phase. But then, of course, so somehow, on average, it stays more or less straight. But then there are all sorts of random effects, right? So somehow, these liquid crystals, sort of microscopically, they are actually kind of some strange, long, rod-like molecules. And so there are some random effects depending on how these things are aligned. And so, there might be some places where this thing moves a little bit faster and some places where it moves a little bit slower. And so after a bit, it doesn't look completely straight anymore, but it sort of, starts to look a little bit wobbly like that. Okay, and then it starts to look more and more wobbly. And what you're interested in then is, as a probabilist, it's not so much, the straight line, but it's the wobbly bits, right? So because they are the ones that look random, and we're interested in the random bits, right? So somehow here, that's what you see after a while, right? So this is an actual experiment where you just do this, and then you take pictures. And color here is time, right? So in some sense, this is just several pictures put on top of each other with different colors. Okay? And you're interested then in understanding how these fluctuations behave. So here is a similar experiment where what you do is actually take a sheet of paper and then, well, you do more or less the same thing. So you zap a laser beam at the bottom of the sheet of paper, and then it puts it on fire, right? And then the fire actually moves up, and you look at the position of the flame front as a function of time. And what you do is you use the sort of paper, it's a bit like cigarette paper, right? So it doesn't really burn, it just makes a nice kind of flame front, so it doesn't start to make big flames or something, right? So it just starts to kind of consume itself in a nice regular way. But again, there's a little bit of randomness that makes it, create these kind of fluctuations. And you're interested in the description of this, right? So then you can come up with, lots of little models, right? So you want to come up with some sort of mathematical model, right? But now the hope is, well, there's this universality business. So this universality business tells you that, well, it shouldn't really matter what kind of model you come up with. They should actually all behave the same anyway. Okay, so you could just as well, so you could just as well come up with this model, which, since that's a Russian speciality, which is the Tetris model. Right? So you take basically a Tetris game, which you don't play. Right? So somehow the the Tetris bricks just fall down and they accumulate and they sort of pile up. Now, okay, this doesn't look like a reasonable model for what I just told you, right? I mean, it doesn't even look like this at all. But actually, if you look from a little bit further away, it looks a bit more like that, right? I mean, so somehow, now if I go a bit further, right, it sort of looks like this. So now it does actually start to look a bit like, some sort of interface that grows and that starts to fluctuate a little bit, right? And so you can kind of, you look from further and further away, you sort of look something like this. And that looks very much like the previous picture, actually. Right? So now you would like to understand, things like that. So what is this supposed to, what are these fluctuations? How can you describe this kind of curve here? Well, basically nobody has any idea. So for this Tetris model, there's basically nothing is known, actually. I mean, okay, so of course the Tetris model is not very serious one, so I don't think there are many papers written on that, even though there is a nice survey article in the notices of the AMS, which has these Tetris bricks on the cover, so that's in this context. So, but there is a sort of more well-known model among physicists, which is called Ballistic Deposition model, and this one has been studied a lot by physicists. And it's basically the same, but it's a bit less funny. So this has been studied a lot in the physics literature, but almost not at all in the mathematics literature. Right? So in the mathematics literature, almost nothing is known about that model, or somehow a similar model. Of course, you can make sort of little experiments, right? So you can come up. So here there are somehow 3 models of a similar type. So the one in the middle is this ballistic deposition one, which has been studied a lot. And so you see this really looks a bit like what you saw in the Tetris model, right? It really looks the same. The others also look somewhat similar. And now what happens is that, well, it turns out that some of these models, so there are very, very few ones, so there are 2 or 3 very, very special models. They have some additional structure, which we call somehow integrability, or they have some kind of integrable structure, which allows people to compute certain things exactly. So there are kind of miracles occurring in some of these models. And these miracles make it possible to compute certain things and to take limits as, you know, time goes to infinity, or as the thing, you know, as you zoom out somehow. And so there has been, you know, quite a lot of work in the last 10 years or so by a number of people to look at these very, very specific models and to try to compute what happens when you zoom out, when you look at large scales for these very specific models. And then, of course, you can always argue, well, universality, and therefore everything else should look the same somehow. So now there's a very recent, so actually this is a result from this year by a group in Canada, which obtained a full characterization of this limit for one so there's one of these very nice models, which is somehow even nicer than all the others. And that one you can compute everything, and so you can have a full characterization of this limit. So in some sense, that's the analog in this context of, you know, the characterization of Brownian motion by Gaussians, except that it's a result from this year instead of from 100 years ago. And the characterization is quite a bit more complicated. And it's not in terms of Gaussian distribution. So these fluctuations, they are not actually Gaussian. They are not symmetric either, right? So somehow the situation is not symmetric. So the fluctuation doesn't go in the same way in this direction and in this one. Okay. So now what I've been interested in is somehow to understand this question of universality, right? So now there are these certain models that are very special for which you can compute everything. And well, so there's one model for which you can compute everything. So there are a few other models where you can compute lots of things. And then you can check that these lots of things are the same as the everything that you can compute for the other model. So you somehow have hints that there is this universality, right? So there are there's a few different models where you can compute things, and you see you get the same answer. But it doesn't really tell you why you get the same answer, right? I mean, you can make some, you can come up with hand-waving explanations, but being mathematician, you would like to actually have a sort of, hard explanation. And so it turns out that there's a class of model which is much better understood, which is the ones where, so here the situation is very asymmetric, right? So the thing moves on average, it moves in one specific direction, okay? And so this direction plays a different role from this direction, right? So you move in one of the two and not in the other one. Or like in the Tetris bricks, it was clear somehow they only go up, they never go down, right? So there's a class of models which is much better understood, which is models where the fluctuations can go both ways. Okay, so there are some situations that are somewhat similar, where the two regions play completely symmetric roles, and then there's no reason for the fluctuation to go up rather than down, so things are somehow much nicer, much more symmetric. And in that situation is much better understood. And there in particular, one has a very easy, complete characterization of what you expect the behavior to look like at large scales. And there again, it's completely described in terms of Gaussian distributions. Right? So again, it's very much like the Brownian motion, except that this time it depends on space and time. And so actually, for any fixed instant of time, what you see as a function of space really is a Brownian motion, except that it's a Brownian motion that furthermore sort of wobbles around. Okay. And so then you could say, well, what you might want to do is try to do something, some sort of perturbation, is to say, well, I start from something which is symmetric, and then I make it slightly asymmetric. So I make it a little bit more likely to go up than to go down, right? So that now I break this symmetry between these two regions, but I do it just a tiny bit, right? So you just make it a little bit more likely to go up than to go down. And so then what do you expect? Well, if you start to zoom out, if you don't zoom out by much, this shouldn't have too much of an effect, right? So it shouldn't really make much of a difference. And then you should still see this Gaussian object, which is easy to describe. But then, as you zoom out further and further, well, it might be that at some point, if you look at what happens, really far out, then you do actually start to see an effect of the fact that you've changed, you've broken this symmetry between these two regions, right? And it turns out that that's the case, right? So as you zoom out, there comes a point where you start to see what people call a crossover. So you start to see a change of behavior basically from one universal object to another universal object. So you have some change of behavior between these two. And, well, the claim is that this change of behavior itself is also universal. Okay, so that what you see, if you look at the scale at which you start to see both effects, what you see is always the same and doesn't really depend on the model. Okay? And so what you see is supposed to be described by something called the Kpg equation, which was studied by Kadar, Parisi, and Zhang in the 80s. And so that's sort of, at least for the mathematicians in the audience, that's the equation. So it's, so here h, right, so you have a x-axis here, and you have a h here, and h is basically the position here, right, of the interface, which depends on space and it depends on time because it's a movie, right? And it's supposed to evolve according to this equation. So there's something here which is actually like this heat equation that Fourier introduced. Then there's some nonlinear term here, and then there's here something which is called white noise, and that's the thing that makes it random somehow. Yeah? There's actually a way you can understand this term here. It really comes from the fact that, what happens is that the interface doesn't really know that you've put the whole thing into a coordinate system, right? And so if somewhere it looks a bit like that, then of course it wants to actually move in this direction, right? It doesn't care about the fact that you've put an, coordinate system here in order to describe it by a function. So maybe the coordinate system is slightly skewed. But then if it moves in this direction, you see if it moves by, say, 1 in this direction, since you're measuring its height vertically, you have the impression that it moves by a little bit more, right? And so you get, by Pythagoras' theorem, you sort of know by how much it moves in that direction. It's something like square root of 1 plus the slope squared by Pythagoras. And then if you do an approximation, you say the slope should be small. Also, then to first order, it's actually given by just this square. Okay, so this is sort of like a first order term in a Taylor expansion. And so here is a, oh no, that's the other movie. So here is a movie of sorts, right? So that's what this equation looks like. So this is somehow what the solution to this equation looks like. And so now, so one thing you see here is that if I stop the movie for a second, So if you make a snapshot at a fixed instant of time, well, this looks a little bit like what we saw earlier, right? So it looks a little bit like the Brownian motion that we saw earlier. Okay? That's actually a theorem. So you can show that, yes, it does really look like a Brownian motion. And now remember the other thing that we've seen, which is that everywhere the Brownian motion somehow looks like one of these square root sort of curves, right? So so Brownian motion is somehow a very jittery sort of curve like that, but at every point it doesn't really have a slope anywhere, right? So because locally it doesn't look like a straight line, locally it actually looks somehow like a square root, a bit like that, everywhere. Okay. So, whoops. So that's kind of a problem, because you see, if you look at this equation here, well, there's a square of the slope here that shows up, right? But I just told you that it doesn't have a slope, right? And it really doesn't have a slope in the sense that it looks everywhere like that, right? So it looks like the slope is vertical. Okay, and if it's vertical, that means that the slope is infinite. And so, you know, if something is infinitely big, maybe there are some sort of crazy cancellations, but if you square it, well, then it's an infinitely big thing that's positive. So there's no, no possibility for crazy cancellations anymore. And so this is clearly a problem, right? But still, one expects that somehow there's some kind of meaning to this. And this is supposed to be sort of universal. Okay, so so you can actually prove results that go in this direction. Okay, so for example, one thing that we showed, well, so there's a series of papers. So there's one with Jeremy Costel and sort of a couple of other people. Is that you can look at a relatively large class of models, and they are sort of models that have this property that they are something which is symmetric plus a small perturbation that makes it non-symmetric. And the small perturbation is this small parameter epsilon here. And then you can actually prove that for all models in that class, if you zoom out, and you zoom out by the correct amount, and you somehow recenter things correctly so that the curve more or less stays put and doesn't sort of fly away, well, then indeed, this thing actually converges to a random limit, and that random limit is in some sense described by that equation. Okay? But of course, that equation, as I just mentioned, right? So the equation actually itself, strictly speaking, doesn't really have any meaning at all. Right? So the equation, it has somehow, sort of a square of an infinite slope showing up in the equation. And so, it doesn't really have any kind of meaning. And so you have to, work in order to give a meaning to this equation, right? So somehow the contribution that I made in the last few years is to, basically set up a theory that allows you to give meaning to things like that in a rather systematic way. And somehow the basic tool is to try to do, right? So you try to do something like Taylor expansions, right? So usually when you have a nice smooth function, well, you say, well, maybe, so it has a value, but then it has a slope. So maybe, you can kind of approximate it by a straight line. But then it also has a second derivative. And so you can get an even better approximation if you approximate it, say, by a parabola. And then it has a third derivative. So you can get even a better approximation by taking sort of a cubic function, etc. Now, of course, here it doesn't work because, the functions sort of look a bit ridiculous because they kind of look like this. And so, there's no way that you're going to get better approximation by playing around with lines and parabolas or things like that. But it turns out that here you can actually build sort of random functions that themselves look like this, sort of look very spiky like that. So that, the solution is, you can actually approximate the solution by, some of these random functions. And then you can exploit this in order to give a meaning to this nonlinearity. Okay, but so I think I've taken enough of your time, so I'll stop here. And well, thank you very much.
Well, thank you for the lecture. And can you say that the function that you were talking the last time are some kind of the generalization of Taylor expansion or Fourier expansion for a more wide class of function, including randomness.
Yeah, so it's some sort of generalization of Taylor expansion, but it's a okay. So the difference is Taylor expansion is somehow always the same. Okay, I mean in the sense that you take any smooth function, well, you're always going to approximate it by linear functions, parabolas, etc. And it's always linear functions, parabolas, and so on. So here, the actual somehow random objects that you use to approximate it, they depend on the problem you're considering. So for this particular equation, you have one way of building these functions that play the role of the Taylor polynomials. But then if you look at a different problem of a similar type, you will have different kind of random functions that are going to play the role of Taylor polynomials for that problem. Right? So they are more problem dependent, whereas the Taylor approximations, they are not problem dependent. It's always polynomials. Right? So that's
a simple example.
Yeah, so I can show you another example. I mean, I can show you another movie. So where is the other movie? Sorry, maybe here. Okay, so this is another example. So this is something which looks somehow more like an Ising model, but it's like a sort of semi-mean field version. And so in this case, I'm not going to write out the equation, but somehow, okay, so first you see space is two-dimensional instead of one-dimensional. The other thing you see is that this thing sort of flickers, right? I mean, so it's somehow, there are all these dots, right? So even you have lighter, so color here means height, if you want. But you see it's very irregular. So here actually the limiting object is not even a random function, but it's a random distribution. Okay, and so clearly it's not going to be the same kind of objects that locally describe it. But
I was speaking about an example of new Taylor expansion of this random Taylor. Analog of Taylor expansion.
Oh, yeah, so you cannot, right, so you cannot typically, okay, so typically you cannot write down explicit formulas for the coefficients in this expansion, okay, and then, okay, so I think it's
the Taylor expansion with random coefficients, what are you speaking about?
Well, so both the coefficients would be random, but it's really the objects that take the place of the Taylor polynomials that are random. Right? So it's not a Taylor expansion in the usual sense of Taylor expansion, right? In the sense that you don't write things as sums of, say, x minus x0 to power k also, right? So you replace x minus x0 to the power k by random objects themselves.
Maybe I can rephrase the question in another way. So you have one random object that you describe with other random objects. Where did you gain anything?
Ah, that's a very good question. Yes. Is that these other objects are much easier to describe.
Okay.
Right?
So yeah,
in the same, right? It's exactly the same thing when you do Taylor expansions, right? It's because polynomials, you understand them very well, right? And so the same reason.
Yeah. So more questions? Deviation principle tells you not only that what typical events have low probability, but they have positive probability as well. Yeah. Okay. Well, I have two questions from person.
It is connected on how you go from a discrete model to the continuous model in sense on that example of Tetris. Well, the Tetris is a discrete model, and in fact, when you get the function in partial differential equation, it is continuous. And how are they gained one to each other?
Yeah, right. So that's okay. So that's the hard bit. Well, one of the hard bits. But okay. So first, this somehow theory. So at the moment we don't know how to apply. So the Tetris model is not of this form, right? So it's not something which is almost symmetric. Okay. So this theory that I just described, it works in this situation where you look at things that are almost symmetric and you look at this correct crossover regime. So the Tetris model is not of that form. But there are some discrete models that are of that form. And then, yes, so there's, so in some situations, so I mean, this is something that we still work on, right? So it works in, so there are some situations where the discrete model already looks, you know, relatively close to the kind of continuum model that you want to get. And then in these situations, you can set up basically a discrete version of the whole thing, and you have a, you know, and then everything kind of behaves very well. There are many discrete models that don't come in a form that make them sort of look similar to the kind of continuum model that you get in the limit. And there you have to work much harder. So there at the moment, it's still very ad hoc. So somehow there are very few models where things work, and then, but there's no good, very general theory.